The question says that a long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 seconds, what is the induced EMF in the loop while the current is changing? So here there is a small loop of wire of area 2 centimeter square is placed inside a solenoid. So just imagine that if solenoid is seen from its left or right along the axis as this, then there is a small loop of wire of 2 centimeter square placed inside the solenoid. Now we have to find out what is the induced EMF in this small wire, subjected that the the current in this solenoid is changing from 2 ampere to 4 ampere in 0.1 second. Now if the current is changing, then obviously the magnetic field is going to be changing. Now if magnetic field is going to be changing, then there is a flux that is changing inside this loop as well, and flux is changing with time, so there will be induced EMF. Now Faraday's laws of electromagnetic induction says that the induced EMF E in the closed loop is proportional to the rate of change of magnetic flux phi b through the loop, and that is given by induced EMF is equals to minus d phi by dt. Now magnetic field inside the solenoid is given by B equals to mu naught Ni, where mu naught is the permeability of the free space, N is the number of turns per unit length of the solenoid, and I is the current. Now magnetic flux is defined as phi b equals to B dot A, that is the dot product of magnetic field and the area vector. Now for loop normal to the solenoid, as in the case of our question, theta is equals to 0, so the dot product will result out to be BA, as cos theta is equals to 1. Now let's calculate the induced EMF. So as we knew that induced EMF is given by minus d phi by dt, so we have to calculate the change in flux and we have to divide it by time, duration of time. So change in flux, we can see that, and since current is changing from 2 ampere to 4 ampere, so this value determines the delta T, and this is the number of turns per unit length in the solenoid, and this is the mu naught. So this results out to be the magnetic field of the solenoid, 4 pi 10 to the power minus 7 multiplied by 1500 into 2.0. So here 1500 comes from this data that has been given in the question, 15 turns per centimeter. Now if we divide, it has been given that 15 turns per centimeter. Now if we turn this centimeter to meter, then we will get 15 meter equals to 100 centimeters. So we will have to multiply it with 100. So we will get 1500 turns. So that's how we got 1500 multiplied by the area of the coil, that is 2 into 10 to the power minus 4 Weber, divided by time, duration of time, that is 0.1 seconds. So here we will get 7.54 microvolt. Thank you.